When you look at your code, it feels sequential. One instruction runs, then the next, then the next. But modern CPUs are not designed to execute just one instruction per cycle. They are designed to execute multiple instructions per cycle. That design approach is called Superscalar architecture. In this video, we're going to explain what Superscalar means, why it exists, how it works at a high level, how it connects to pipelines and out-of-order execution, and why it is one of the key reasons modern processors are so powerful. Let's start with the basic idea. In a simple processor, one instruction is issued into the pipeline each cycle. That means, at best, one instruction completes per cycle once the pipeline is full. But what if the processor has multiple execution units? For example, 2 arithmetic logic units, a floating point unit, a load/store unit. If only one instruction is issued per cycle, many of those units sit idle. Superscalar architecture solves this by allowing the processor to issue multiple instructions per cycle. Instead of dispatching just one instruction into the pipeline, it may dispatch 2, 3, 4, or more, depending on the design. That is the core idea, multiple instruction issue per clock cycle. Now, this doesn't mean the CPU magically executes everything in parallel. There are constraints. Instructions must be independent. They must not depend on each other's results. There must be available execution units to handle them, and the processor must detect all of this dynamically. This is where Superscalar architecture builds on the ideas we've already covered. Let's connect it to pipelines. A pipeline allows overlapping stages of different instructions. Superscalar extends that by having multiple pipelines side by side. Imagine instead of one pipeline, you have 2. In one cycle, the CPU might issue 2 instructions. Instruction A goes into pipeline 1. Instruction B goes into pipeline 2. If both instructions are independent and there are no hazards, they can execute simultaneously. Now extend that further. Modern processors might have multiple integer units, multiple vector units, multiple load/store units. Superscalar design is about feeding those units efficiently. Now let's connect this to out-of-order execution. Out-of-order execution allows the processor to find independent instructions dynamically and execute them as soon as their inputs are ready. Superscalar architecture provides the hardware capacity to execute multiple such instructions at once. Without out-of-order scheduling, superscalar design would be limited. Without superscalar hardware, out-of-order scheduling would have fewer opportunities to exploit. These two concepts work together. Now let's explore what makes superscalar design challenging. Issuing multiple instructions per cycle requires the processor to analyze instruction dependencies very quickly. It must determine, are these instructions independent? Do they read or write the same registers? Do they access the same memory locations? Are the required execution units available? All of that analysis must happen within a single clock cycle. This requires complex hardware logic. Now let's discuss instruction-level parallelism. Instruction-level parallelism refers to how many independent instructions exist in a program that can be executed simultaneously. Superscalar processors attempt to exploit that parallelism automatically. For example, consider this sequence. A equals B plus C, D généralement E plus F. If these two operations do not depend on each other, they can execute in parallel. A superscalar processor may issue both additions in the same cycle to 2 separate arithmetic units. But consider this sequence. A equals B plus C, D viennads R, A plus F. The second instruction depends on the result of the first. These cannot execute simultaneously. The processor must respect true data dependencies. So superscalar performance depends heavily on how much independent work exists in the instruction stream. Now let's talk about width. When we describe a processor as 4 wide or 6 wide, we're referring to how many instructions it can issue per cycle. A 4 wide processor can issue up to 4 instructions per cycle. In theory, that could mean up to 4 instructions completed per cycle. In practice, actual throughput is usually lower due to dependencies, cache misses, and branch mispredictions. Now, let's introduce another important concept, dispatch, and decode width. To issue multiple instructions per cycle, the CPU must fetch and decode multiple instructions per cycle. This means wider instruction fetch units, wider decode units, more complex scheduling logic. All of this increases hardware complexity and power consumption. This is why superscalar design is a trade-off. More width means more potential performance. But it also means more complexity, more silicon area, and higher power usage. Now let's connect superscalar architecture to pipelines again. Each pipeline handles an instruction through stages like fetch, decode, execute, memory, and write back. In a superscalar processor, there are multiple execution pipelines operating in parallel. For example, 2 integer pipelines, 1 floating point pipeline, 1 memory pipeline. The scheduler decides which instructions go to which pipeline. If an instruction requires integer arithmetic, it goes to an integer unit. If it requires memory access, it goes to a load/store unit. The processor must balance work across these units efficiently. Now let's address a common misconception. Superscalar does not mean multi-core. A multi-core processor has multiple independent cores. Superscalar refers to a single core that can issue multiple instructions per cycle internally. Even a single core can execute multiple instructions simultaneously if it is superscalar. Another misconception is that superscalar guarantees maximum parallelism. It does not. The amount of parallelism available depends on the program's structure. If the code has many dependencies or frequent branches, the processor may not be able to issue many instructions per cycle. Now let's connect this to branch prediction. If a branch is mispredicted, the pipeline must flush. In a superscalar processor, multiple instructions may have been issued along the wrong path. This makes misprediction penalties even more expensive. So as processors become wider, accurate branch prediction becomes even more important. Now consider memory latency. If multiple instructions depend on memory loads and those loads miss the cache, execution units may sit idle. Superscalar width does not eliminate memory bottlenecks. This is why memory hierarchy, caches, prefetching, latency hiding, is critical in high-performance CPUs. Now let's zoom out and connect everything in the execution series. Instruction dispatch determines what instruction comes next. Branch prediction guesses control flow. Pipelines overlap instruction stages. Out-of-order execution rearranges independent instructions. Superscalar architecture allows multiple instructions to execute per cycle. Together, these mechanisms exploit instruction-level parallelism automatically. They allow sequential programs to run much faster without requiring the programmer to manually schedule instructions. At a deeper level, superscalar design reflects a fundamental reality of computing. Hardware is capable of parallel execution. Software often appears sequential. The processor bridges that gap dynamically. When you write ordinary code, the CPU analyzes it, finds independent work, schedules it across multiple execution units, and executes several instructions at once. All of this happens in nanoseconds. But there are limits. Instruction-level parallelism is finite. At some point, adding more width provides diminishing returns. This is one reason why processor design also evolved toward multi-core systems and vector processing. Superscalar architecture is about extracting parallelism within a single instruction stream. It is one of the foundational techniques that define modern CPU performance. If you want to go even deeper, the next step could be exploring vector units and SIMD execution, or shifting focus to the memory hierarchy and CPU caches, where another major layer of performance complexity exists. But for now, you can summarize superscalar architecture like this. A superscalar processor can issue and execute multiple independent instructions per clock cycle within a single core. And that capability is one of the key reasons modern processors are so fast.